Hey, this is a review video of Unit 2, which was our unit called Number, and just has a bunch of concepts that you're going to need every year in math. They're like your essential number sense skills. Okay, so we started with number sets. So these are just talking about like different kinds of numbers. So a long time ago, they had these things called natural numbers. Well, we still have them. But it's where kind of like 0 wasn't considered a number yet. It wasn't like invented. So natural numbers just contain the numbers 1, 2, 3, 4, etc. Only whole numbers, no fractions, no decimals, and no 0. Those are natural numbers. Whole numbers are the same thing except they include 0. So these are whole numbers. They're very similar to natural numbers. They just also include 0. Integers, again, very similar to whole numbers, except they also include negative numbers. So actually our list goes that way. So all the negative numbers, all the positive numbers, as long as they're whole numbers, they're not decimals, they're not fractions. And then rational numbers include a lot of the numbers that are missing from above. They include all of the numbers from above as well, like -3 is a rational number also. But rational numbers are numbers that you can write as fractions. So for example, 5/2 is a rational number. You can also write 5/2 as 2.5. So rational numbers can be written as fractions, and then they can be turned into decimals too. The number 6.4 is a rational number. The number 0.5, because you can write that as a fraction. 1/2, the number, any fraction, 20/3, 4/5, like any number that can be written as a fraction is a rational number, but it can also show up as a decimal. The only decimals that aren't rational numbers are like these crazy non-terminating, non-repeating decimals. So like, for example, the number pi is irrational. It's like 3.14159, I don't know the rest of it, but it goes on forever. So you actually can't write it as a fraction. You can approximate it as a fraction, but you can't write it as a fraction. The square root of 2 is an irrational number. If you actually square root it, it's a decimal that just goes on forever and ever. And then real numbers are actually all of the above numbers. Real numbers include all of these things. Yeah, okay, that's it about number sets. Limits and infinity was kind of a weird topic. It was just like just looking at patterns is what limits were. So like if you looked at this set, 4.1, 4.01, 4.001, 4.0001, it looks like this data set is actually just approaching the number 4. The more zeros you add in here, the closer it's starting to look like 4. So this set is approaching 4. Whereas this data set, 1, 2, 3, 4, 5, I assume what's going to come next is 6, 7, 8, 9, 10, 11. When would it stop? Probably never. So I'm guessing this data set's actually approaching infinity. So this was kind of an odd topic, but you're just looking at patterns and numbers and seeing what they seem like they're approaching. So the strategy I would take for these is I would try to think like, what would come next? I think 0, 0, 0, 0, 1. What would come after that? Oh, I guess there'll be another 0. And that number is looking more and more like the number 4. Exponents, this was just like learning what exponents are. So if you have a little exponent here, that just tells you how many times you're going to multiply this big number, which we call the base, by. So I have 5 2's, 1, 2, 3, 4, 5. So I have to go 2 times 2 times 2 times 2 times 2. So 2 times 2 is 4. Multiplied by another 2 is 8. Multiplied by another 2 is 16. And then another 2 is 32. sometimes we want to evaluate stuff with exponents. So this is 4 times x to the power of 3. If x is 2, let's see what that equals. We'd have 4 times 2 to the power of 3. So I know according to BEDMAS, I have to do an exponent before I multiply. So I need to take care of this before I multiply by 4. So this will become 4 times 2 to the power of 3, which I know is 2 times 2 times 2, which is 8. And then 4 times 8 is 32. We also learned about scientific notation, which is a way to write really big and really small numbers. So 32 million, I can write as 3.2 times 10 to the power of, picture me putting a decimal here. How many times? 1, 2, 3, 4, 5, 6, 7 to the power of 7. So what I did was I'm taking this decimal place and I'm moving it over to make that number 3.2. And then when I multiply it by 10 to the power of 7, that actually moves the decimal back out. So this number is equivalent to this number. Exponent laws, this was like a whole, this is a tricky topic. So there was like 5 exponent laws that we learned, I think, or 4. So one of them was multiplication. So when we're multiplying two things that are the same base, we can add their exponents. So this will become x to the power of 9. When we're dividing two bases that are the same, we can subtract the exponents. So 8 minus 2 is 6. I'm going to go over to this one because this is a very similar one, except these numbers, 9 and 3, are just regular old numbers. So I'm not going to subtract them, I'm actually dividing them. 9 divided by 3 is 3. Now this one's weird. It's like x to the power of 4 divided by x to the power of 6. So I know I subtract my exponents. 4 minus 6 is x to the power of negative 2. Then we also learned that you can't really leave an exponent negative. This is a tricky concept in grade 9. But what we can do is we can turn that into a 1 over x to the power of 2 to make it positive. And then we can actually just write this as one fraction, 3 over x to the power of 2. This one is our power of a power law. So you have to apply this 4 to each term in the bracket. So it becomes 2 to the power of 4 and x to the power of a power law says that we multiply the exponents. So 3 times 4 is 12. And then I can actually solve that. 2 to the power of 4 is 2 times 2 times 2 times 2, which is 16. X to the power of 12. So these are my exponent laws. Oh, the one I missed is at 0. So if you have anything to the power of 0, that always equals 1. That's our exponent laws. Okay, we also learned about fractions. When we add fractions, we need the denominators to be the same. So when we add a third plus a third, we get 2/3, which can be written like that, 2 over 3. And then if their denominators are not the same, we need to make them the same. So we can multiply an entire fraction by something just to make an equivalent fraction. So I can take 2/3 and represent it as 4/6 by just multiplying the top and bottom by 2. So I changed 2/3 into 4/6, which I could totally do, right? Because if I have a third, picture that. This is split into thirds to make a whole. If I have 1/3 and I want to write it as 6, well, 6 would just be like 1/3 split in half, right? Because now I have, that's like 6ths. So 1/3 is equal to 2/6. So if I have 2/3, that's equal to 1, 2, 3, 4/6. That makes sense. And then when I add fractions, I can just add their numerators. So 4 plus 5 is 9. So altogether, I have 9/6. And I know from my little diagram here, if I have 6/6, that makes a whole. So I have one whole at least because I have 9/6. But if I take my 6/6, I can have 1. And that means I have 3/6 left over.
What was that for?
And this might be too crazy, but if I have 3/6, so that's these three. If I have 3/6, that's also like the same thing as saying a half. So I can actually write 1 3/6 as 1 1/2. So that's like changing something to a mixed number. Okay, I'm sorry, this might be getting weird, but I'm also going to show you this. If I want to keep my answer as a fraction, that's also fine, 9/6. But I should always reduce fractions to lowest terms. And it turns out these are actually both divisible by 3. So if I can ever divide a fraction by something, I'm going to do it. So 9 divided by 3 is 3, and 6 divided by 3 is 2. So that's actually 3 halves, which is the same as 1 1/2. Okay, cool. That's it for oh no, just kidding. We're also multiplying fractions. To multiply fractions, you can just multiply straight across. And the denominators do not need to be the same. So 2 times 5 is 10. 3 times 12 is 36. And then always reduce to lowest terms. So they're both at even numbers. So for sure I can divide them by 2, which gives me 5/18. And I think that's all I can do. So that's it. That's how you multiply fractions. Oh, I can solve proportions. So these are just like a pair of equivalent fractions. So what happened to 24 that it turned into a 4? Well, it looks like it got divided by 6. So I can do the same thing to the top. I can just divide that by 6. So I know that actually x must equal 3. So 3/4 is the same as 18/24. That makes sense? We also talked about integers. So they're just negative and positive numbers. So 2 plus 3 would be 5. And then 5 minus 4 would be 1. So just like adding and subtracting. Sometimes they're written as word problems. At 3 p.m., the temperature outside was 10 degrees. Okay. Every hour, the temperature drops by 2 degrees. What would the temperature be at 7? So if you're not really sure, just like logic this out. 3 p.m., 4 p.m., 5 p.m., 6 p.m., 7 p.m. So it says every hour, the temperature drops 2 degrees. So it would be like 8 degrees, then it would go to 6 degrees, then it would be 4 degrees, and then 2 degrees. That's your answer. That was actually a question from the test, which more people got wrong than I thought would. Bed myths, we kind of just touched on this. It's just the order that you have to do things in. So the first step would be brackets. So let's do whatever there needs to be done in the bracket. So what's 1 minus 4? It is -3. So brackets done. Next step, exponents. So I have to take care of this. So I'll just leave everything else the same, and I'll change -3 squared into 9, because that's what -3 times -3 is. Exponents are done. Division and multiplication can be done next in any order. And it looks like I only have multiplication. 5 times 9. If there's no sign in between stuff, that always indicates multiplication. So 5 times 9 is 45. And now I just have adding and subtracting left, which I can do in any order. So I like to just do it in the order it comes. So 3 plus 45 would be 48. And then I just have to subtract 10 from that. So that's 38. Final answer. And that's the majority of the stuff from number